Well, howdy. Now, here is the last of your homeworks. What we've got is a glider, like you may have done in lab, may not have, coming over here and hitting this other guy. And then when this big glider hits little glider, they're both going to go off in the opposite direction, or in the same direction, right? What we know is that the big glider is originally going at 1.5 meters per second. Oops, 1.5. And he's going to end at 0.5 meter per second. And we don't know anything about this guy here. Call that little u. And we're going to want to find those two things out. I'm going to reverse the order of the two things in the homework because one of them's easier and it makes the other one easier if you find it first. So why don't I do that? Let's see. So how do we do this? Well, the deal here is we know the final and the initial for this one cart here. We actually know the initial speed of this cart, which is 0. And we want to figure out what the mass and the speed are for the other cart afterwards. And it's an elastic collision. Now remember, an elastic collision conserves energy. The amount of energy is the same before and after. And that's why we're able to get two different things. We're able to solve for two different things because we've got two different conditions. So all collisions conserve momentum. So we're going to have to conserve the momentum here. And then we're going to also, in this case, because this is elastic, conserve energy. And we're going to need to get both of those two conditions working to solve this. So let's start just by going through each one of those and seeing how far we get in each one of those. And we're not going to be able to solve for u or m in either of them, but we're going to be able to solve for a product of them. So let's do that. Then we'll be able to take those two conditions and combine them and find the speed. So what we have is the mass times the velocity of the original one. I'll use, for the larger block, capital letters, plus the mass times the velocity of the smaller one, which is 0, because it's not moving. So that's the initial total, that's the initial momentum of the system. All the momentum is in the motion of the larger glider. Afterwards, both of these guys are going to be moving, so that same amount of momentum is going to be shared between both of them. So then we'll have m times u. Now the u is the afterwards, that's the 1/2 meter per second here, and m is the same mass as 400 grams. Plus, now I'll use lowercase letters for this other guy, because he's the small glider, he gets the lowercase letters. And so that's m times u, v before, u after. Well, why don't we just plug numbers in? That seems to be a pretty good thing. So we don't want both of these, and we know all of these other things. So just plugging numbers in seems to be a reasonably good way to go. We have 400 grams of stuff over here times the velocity, which is 3/2 meters per second. That's equal to 400 grams for the large glider. It hasn't changed its mass. Times its final velocity, which is 1/2 of a meter per second. I hope I have enough room. Probably should have cut this into more spots. Plus m times u. So this guy, we don't know those guys, we just have to keep them. Multiply these things out, so we have 400 times 3/2, which is 600 grams meters per second, is equal to 1/2 of 400, which is 200 grams meters per second, plus mu. So we can solve for mu. I'll put mu here. That's equal to 600 grams meters per second minus 200 grams meters per second. So that's 400 grams meters per second. So that starts off pretty well. So we can get that product, the momentum, this is just the momentum of this yellow glider, which I've completely covered in red marks, before the, or after the collision. So that's a product of those two things. Now we need to find some other way to express those two numbers, a relationship between them, and then we can get the final answer mathematically. Well, let's do this. We'll have 1/2 mv squared is the initial energy, because it's all kinetic energy. So it's going to be the same expression, 1/2 mu squared on the other side. Again, this is the energy of motion. The yellow box isn't moving, yellow glider isn't moving, so it has no energy initially. So all the energy is originally in the motion of the red cart, the red glider. And then we have the yellow glider, which are the lowercase letters, same expression for the kinetic energy. Well, we have something similar to what's going on here. So let's just put all those things in. We have 1/2 times 400 grams times 3/2 meters per second squared. That's a whole lot of stuff. Is equal to 1/2 times 400 grams times 1/2 meter per second squared. Oops, not enough room. Plus 1/2 mu squared. Okay. So let's see. Let's take those numbers and multiply them together. All right, so let's see. This is 200 times 9/4. It's 100 times 9/2, which is 450 grams meters per second. Squaring both of those is equal to 1/2 times 1/4 times 400, which is 1/2 of 100, which is 50 grams meters per second squared, meters squared per second squared. And I ran into the other equation. Fortunately, it's the next thing I was going to write anyway, because we can't do anything with any of this stuff. Next thing we have to do is add these two, which gives us 500, right? And then multiply by 1/2, which is going to give us 1,000. So, yeah, first I have 1/2 mu squared is equal to, oh, whoops. That should be 400. Well, 400 grams meters squared per second squared. Then we double that, that's actually 800 grams meters squared per second squared is equal to mu squared. But this is mu times u, right? So mu is 400 grams meters squared per second squared times u is equal to 800 grams meters squared per second squared. Oops. So we divide through, and that's u is equal to what? 2 meters per second. Okay. 2 meters per second, that's something we can do. All right, so that's going to screw me up because, you know, that's, do 800 divided by 400, that's what I wanted, is the 2 meters per second. Okay, so I don't have to go any farther except to note that for some reason when I did this before, I added those instead of subtracted. So that's 800. Okay, so now that we have those, we need to find the mass of the other cart. Well, we just come back to this one, so we know that the mass is equal to 400 grams meters per second over 2.0 grams meters per second. Well, that's just 200 grams. Right, so that's basically what we need, except, like I said, I screwed up. 2.0 meters per second and 200 grams. All right, so that's more or less what we need for this guy. And that's how to do that problem. That's problem 1. Now this is 10 minutes in, so let's see how we handle problem 2. Oops. There's the answer. I'm sorry. They're out of order. That's what I get for putting these together at 7 in the morning or whenever I did. So I've got more errors. Oh well. I need to get this out to you. I don't have time to worry about errors. All right, so what I do, I have a grinding wheel here, and I'm going to spin it up to its operating speed, which is 955 revolutions per minute. It's a disk, a solid disk, and we just want to figure out how long it takes to do that and how many full rotations, how many full times it goes around here to get to its operating speed. How many times does it take to do that to get to 955 revolutions per minute? Well, we like to do things in seconds. We like to do things in radians, right? So we're eventually going to have to use like the acceleration, right? The angular acceleration is defined the same way as the linear acceleration. So the final angular speed, which is this 955 RPM, is equal to the angular acceleration here, which we're going to get from the torque times the time. So that means t is going to be equal to omega over alpha. So we have to find those two things. Well, omega is just this, but to do this here, we need this instead of RPM, we need radians per second. So that's a conversion problem. So let's just do the conversion down here. And then that will disappear later on. Let's see. What am I doing? Okay, I'm doing the conversion. So that's 955. Omega is equal to 955 revolutions per minute, RPM. So we need to do the conversion. Revolutions, want to get rid of one revolution. We need 2 pi radians. That's an important political statement. 2 pi radians will balance out any revolution. And then every minute is worth 60 seconds. So let's see what happens here. If we do 2 pi over 60, that's pi over 30. And I think I'm going to have to do that in the calculator. And that's about 100 radians per second. Which is why it's such a strange number. So I could end up with a nice number for that. So this is 100 radians per second. How about the torque? Well, the torque is tau equals I alpha. That's how we're going to figure out that from the rotational analog to Newton's law. We know what the torque is. We need to find that moment of inertia. This should have been moment of inertia. All right, and how do we do that? Well, I is equal to 1/2 mr squared. Why is it equal to this? It's because this is a solid cylinder, right? So whenever you have a shape like this, all you have to do is look up. I mean, it's rotating around its center of mass. All you have to do is look it up in the table, right? There's a table in your book. There's a table online, and if you need the moment of inertia, it's going to be there. So it might be worthwhile putting that table in your notes. Okay, just saying, there might be a reason why you're allowed to have notes on the exams, and that actually probably is it. And so we can figure that out from this guy over here, and we said this is spinning, this wheel, it's not a spinning wheel, it's a grinding wheel, is 2 kilograms, and its radius is 5 centimeters, 0.05 meters, 1/20th of a meter. So we square that, and that's 1/400th of a kilogram meter squared. So that's I. Alpha is going to be equal to tau over I. Tau is 0.25 Newton meters squared. This is, so that's 1/4, and I is 1/400, so we have 400 over kilogram meters squared. It's 400, not 4,000. So that's 400 times 1/4. Well, that's 100. Inverse square seconds. 1/2 squared. So that gives us 100 radians per second, so 1/s over 100, 1/s squared, which is equal to 1 second. So it'll take 1 second to speed up to 955 RPM with 1/4 of a Newton meter torque. Okay, so, oops. Sometimes the thing's a little unresponsive. And I don't know if it's because I hit the wrong spot on the screen or it is just waiting. All right, so that's the same thing we've done all through here. So that's all good. Now, how many full rotations does it take for the wheel to get there? So this is a funny story. Okay, so probably shouldn't tell funny stories on the internet. Let's see. So, New York has a high stakes exam at the end of its high school experience. It's called the Regents exam. And 1 year on the Regents exam, or maybe it was a couple of years, but at least 1 year, they had this math question, right? And it's pretty simple. Okay, you have 200 students. You can fit 60 students on a bus. How many buses do you need to take all those students to, the museum or whatever? So a lot of students just looked at that and they said, I've been doing this math over and over. I've been studying this over and over. I know what you do, right? You take the number of students that you have divided by the number of students per bus, and that's going to give us, we need 1, 2, 3, and 1/3 buses. That's what they said. We need 3.333 buses. Turns out having 1/3 of a bus is just about as good as having no buses at all. So you really need 4 buses, right? In this case, we want to do the full number of full rotations. That's actually going to screw me up a little bit here because it's a little bit too much to get through to do this 1 second's worth of stuff to get to the 955 RPM. So basically that means I'm going to truncate things. Now the first thing we need to do is we need to figure out how much angle it goes through. 1, 2, 3, how many times it goes through like that. So let's see, theta is going to equal the same thing that we had for kinematics again. 1/2, your position is equal to 1/2 your acceleration times time squared. All right, in this case, your acceleration was 100 inverse square seconds times your time, which is 1 second squared. So that's going to be 50 radians. All right, so that means this is 50 over 2 pi. This is why it's an unfortunate choice, because that's going to be 7.95, but we need to take the floor of that, 7 full rotations to get there. It didn't quite get through that 8th one, and that might screw you up on your problem. So just wanted to let you see that. So what happened there? We just, in order to find that time, we had to use angular kinematics, which is just like regular kinematics with angular variables. Then we needed to use the torque to find the angular acceleration and the moment of inertia. To help us out with that. Things wobbling on my knee. And we needed one sort of conversion here to get us from revolutions per minute to radians per second. Then we came down here and we truncated that number after we found it. That was about it for that problem. Okay, and I think that's the hardest. I think those are the hardest two on your homework. So this time, what we want to have happen is we want to look at a conservation of energy thing. We're going to put this block on this platform. Oh, I don't know what that did. I don't know what that is. It's just... okay. I'm going to put this block on this platform and push it down, then let it go, right? And it's just going to fly up into the air. I'm going to put these 3 springs down there. I just say 1 spring, but it's going to be 600 or 6,000 newtons per meter as its spring constant. Then I'm just going to let it eject this thing way up here. All right. So we're going to compress it a distance x. I'm going to let it fly up here at height h. And what I'm going to say here, which I probably should have said somewhere in there, is I'm going to take x to be much less than h. I'm just going to ignore the x. And we'll see if it was okay for me to ignore the x afterwards. So if 0.1 meters, if 10 centimeters is large compared to this, if it's like, this is only going up like 2 meters, that might be a big number. If it's going up like 10 meters, who cares about the 10 centimeters, right? So we'll see if that's okay here. Because I don't want to do the quadratic formula. And I know you don't want to do the quadratic formula, because that's what would happen if we didn't say that. Okay, so we have UI is equal to UF. I pull this down. At this point, everything is spring energy. And then we need to put the spring energy in there, 1/2 kx squared. That's going to be equal to the final thing at this point. It's all gravitational potential energy, which is mg times h. Okay. So then I come down here, I plug in some numbers, 1/2 times 6,000 newtons per meter times 1/10 of a meter squared is equal to the mass of the block, which is 1/4 of a kilogram, times the gravitational acceleration, which is 9.81 meters per second squared. And, oh, that's why some of these things end up being harder. Okay. And then we need the thing we need is the h. And everything's gone sideways. Okay, I don't know why I'm doing that. All right, so how do we do this? Well, let's see. 2 and that, 3, and then I've got 1, 2 of those guys. So I've got, on this side, 30 newtons per meter, Newton times meters, is equal to 1/4 kilogram times 9.81, which is 2.4 into 18 is 425. We've got a 2, got a 5, we've got nothing left after that. And that's kilograms meters per second squared, which happens to be a Newton times h. And so then we just have to solve for h, which is 30 meters over 2.45245796632, or yeah, just 2.4525, which is too much, but that gives me 12.23 meters, which means that 0.1 meter is less than 1%, so I don't really care about it. So that is this problem. All right, so again, we just started off saying we know what the potential energy is here, we know what the potential energy is here, or the forms of those things are. We've got a bunch of information, we plug numbers in, and that gives us this large number, and we were able to make the approximation x is much less than h. And it's going to be less than 1% of a difference, so we ignore it. We don't have to worry about it. We're okay. All right. Otherwise, there would have been a little bit extra we had to do. All right, so let's see. That was the third one. So what's next? Oh, we're moving. And this one's out of order too? Okay. See, I make the last slide first and then I copy them, but the copy always comes at the bottom. These are... that's just really annoying. Anyways. Okay, so here we've got something that's moving. It's going in this direction, then it's going in that direction. These are very special speeds. They're Pythagorean triples. So if this is the velocity, 4 meters per second this way, 3 meters per second this way, you might guess from life in high school that this is 5, a 3, 4, 5 triangle. But there are other special triangles as well. So, you know, if we're saying that this is 5 meters per second this way and this is 12 meters per second this way, then this is 13 meters per second that way. So I chose special numbers to make my life easier. And that's because we're going to do this initial kinetic energy here, and then we're going to find how much work is done, which will make us find the final kinetic energy. And it's much nicer if I have easy numbers than if I have hard numbers. So I think of these things like what I have to do on a board, not... I wonder how... Well, actually, on this one, it would probably be very bad to try to pull up a calculator. For if I was doing this on my laptop, then it might be fairly easy. Don't distract me like that. I don't want to start writing on my laptop just at the beginning. So let's see, we have v squared, right? So we get that by the Pythagorean theorem here, right? So we have Vx squared plus Vy squared is equal to the V squared. X was equal to 4 meters per second squared, and Y was equal to 3 meters per second squared. Now, because these are Pythagorean triples, I know that this squared plus that squared is equal to 5 meters per second squared, which is equal to 25 meters squared per second squared. Right, so this guy just plugs into that guy over there. So we have 1/2 times 5 kilograms times 25 meters squared per second squared. All right, and so 1/2, oh crap, I'm supposed to change that to 4. Oh well. I wrote the answers with 4. I left the 5 up there. Oh well. Switching it back to 4. Because that turns this into 2, and I know 2 times 25 a lot better than I know 125 divided by 2. So I've got 50 joules. So 50 joules is how much energy is there. And we go back here. We saw before, see, that's what I was using for 4 kilograms. All right, so that's only 3 of the 4 that I've made a mistake on somewhere. Editing is where you make a lot of mistakes like that. You'll learn that, don't worry. Okay, so Kf is equal to 1/2 m u squared, the speed after the turn. And we said that we've got the same thing going on with u squared before here. Or we have to explain that we want work to be using the work kinetic energy theorem, which is the work is the change in the kinetic energy, Kf minus Ki. We already have Ki, so we want to find Kf, and that's what I'm doing here. I've got ux squared plus uy squared over there, which, like I said, was 5 meters per second squared plus 12 meters per second squared. Squares up there. And that is 13 meters per second squared, which is, if I remember these things from high school, 169 meters squared per second squared. So if we come over here, we have 1/2 times the mass, which is 4 kilograms, times the square of the speed, which is 169 meters squared per second squared. That's just like saying that's 2 times 169. That's 32 plus 320 plus 18. So that's 338 joules. So then we can bring this in here, which is 338 joules minus 50 joules is equal to 288 joules. And that's it. That is the problem. So again, first we just found the initial kinetic energy, and that was somewhat aided here. If I didn't know that this was a Pythagorean triple, you could just plug that into your calculator and you'd end up there. And then we need to find the difference between our initial kinetic energy and our final kinetic energy. So we do the same process all over again, only with these other numbers. Again, I use another Pythagorean triple, but you can just use your calculator. And then I subtract over there, and this was supposed to be 4 kilograms. And that's the last, or this is the last one. Let's see how I screwed this one up. So at least I didn't get the first slide off. But once again, I ended up with 2 parts of the question. So in a way, this is more two-parters than usual. Actually, this is another one where we could have just No, I didn't make a mistake. Isn't that nice? Could have just started off with this one, and probably I should have. Remember, the internal energy of the gas is just P times V, right? And that's the pressure, which is standard pressure, which I said was going to be 100 kilopascals, times 100 cc's for the volume. cc is a cubic centimeter. So that's 100 times 100, but this is 100 times 10 to the fifth. And this is 100 times 10 to the minus 6. So that is 10 to the minus 1 joules. 10 to the minus 1 times 100 times, oh, this is 10 to 10 cubed, excuse me. It's 1 times 10 to the fifth. It left the 100 there, so that's cubed. It's a kilo. I'm not allowed to make mistakes now because I've been talking for 36 minutes. I'm not going to redo it. Let's see. Although I made another mistake on this in the slides. Okay, so that gives us minus 3, and then we have 1, 2, 3, 4. That's plus 4, so that's 10 joules. That's pretty good. So the internal energy of this gas is 10 joules. Now we want to use that to find how many atoms are in there. We use the ideal gas law for that, which is PV equals NKBT, KB being the Boltzmann constant. It's something to do with entropy. So PV we just said was 10 joules. N is what we want, is how many atoms. KB is 1.38 joules per kilogram. And I should figure out what, this is, 20 degrees Canadian. So let's see, what is that in Kelvin? So to go from degrees Canadian to Kelvin, that's 20 degrees C plus 273 K is 293 K. And that was times 10 to the minus 23. That minus 23 is important. Okay, maybe at some point I'll be able to get through this again, but not today. All right, N is multiplied by 1.38293. I can't do that in my head. That's 404, and that's close enough, times 10 to the minus 23 joules. Okay, and I guess if we want to make life easier, we have 4.04 times 10 to the minus 21 joules, which means that if we reverse this, we have N is equal to 10 joules over 4.04 joules, so a little bit under 2.5, times 10 to the 21, and that's the whole total number of atoms. And so that's about 2.47 times 10 to the 21. Okay, and so that's the answer. And it did it again. And I don't know what I did. All right, so I could do this through twice. I don't know why I have the right answer here and the wrong answer there. I do know why I didn't. I saw an error and then I didn't correct it everywhere. So let's see. Yeah, what I did is I just calculated the internal energy, and then, which is just the P times B. And then I made that equal to NKT because that's the ideal gas law. That internal energy is shared between N atoms, and the mean molecular kinetic energy per atom is kBT, right? And then I went through and did some stuff. And that got us answers that are close enough for right for today. All right, so let's see. Oh, I'm doing good. I'm even going to be in time for my meeting. So hopefully that's sufficient for you because it's about time for me to go be an adult for a little while. I hope you have a good time. I hope everything works out for you over the summer. And I will talk to you at some other point. There should be a test coming up. Isn't there a test coming up? I don't want to think about that. Bye now.